We've got Sarah McCord up next. Sarah is a scientist with the USDA Ag Research Station out of El Coronado. And Sarah is going to talk to us about data quality in the context of AIM.
Thanks, Scott. So good afternoon, everybody. Thanks so much for joining us today. We've had a lot of talks about different applications of AIM data and different ways that people are using AIM data, and we just wanted to take some time to kind of pull the lid back on what we mean by AIM data. And if you wanted to use AIM data, you know, what comes with the package, what types of steps are we taking in the process of generating that data and storing that data to ensure that the final product of AIM data is as sound as it can be. So I just wanted to review that a little bit for folks who may not be familiar. I'd really like to thank my co-authors, Nicole Capuccios and Sarah Burnett of the BLM National Operations Center, and Jennifer Courtright at Utah State's National Aquatic Monitoring Center. But really, a lot of credit also goes to everyone who's been in the process of creating, storing, using AIM data. Anybody who's touched AIM data has contributed greatly to this talk. So what I'm going to go through first is just describe AIM data and, you know, what comes with the data package. Second, I'll talk about some of the quality assurance and quality control steps that we take as a program with AIM. And then third, I'll talk a little bit about how to access data and to hopefully get more users of AIM data. So to date, we have over 1,400 aquatic AIM plots and over 18,000 terrestrial AIM plots scattered throughout the western United States and into Alaska. The AIM core terrestrial methods, you may have heard this mentioned in other places, but I really want to focus on the methods specifically in this talk. So for terrestrial, we have line point intercept, vegetation height, canopy gaps, and soil aggregate stability. Any number of indicators can be calculated from these methods. And so even though maybe you're hearing a lot of use by BLM about vegetation cover and composition or some of the other indicators that have been mentioned today, know that there's a whole host of indicators that have not been talked about that these data could be used for. And all of these methods are also used by the NRCS's NRI as well as other agencies. So it's a core consistent methodology that then can be compared and combined with other data sets. Similarly with terrestrial, there are 17 core methods, all dealing with various aspects of physical, biological, chemical components. There's also a number of stream covariates. And I forgot to mention that terrestrial also has a set of covariates where we dig soil pits at every AIM plot. And so all of those are considered to be part of the core data package that you get, and any number of indicators in this aquatic suite can also be collected, or it can be calculated. So for instance, off of substrate, you can get all kinds of information about different kinds of fine sediments and how that might be affecting the aquatic systems. All right, so data collection and management, you may have heard some different terms thrown out about how AIM data are collected and how they're stored and how they can be accessed. And for us, we break it down into two different components. We have the field capture aspect of AIM data, and where possible, we like this to be an electronic format. And then we also have the national database, which we view as the storage and delivery mechanism of AIM data. So on the terrestrial side, we have the database for inventory monitoring and assessment, which is an access database. It actually has the ability to store a number of methods beyond the AIM core, but all of the AIM core are collected and stored over the short term in DEMA. And then eventually those data, we move them from DEMA into a national geodatabase called Terrestrial. For the aquatics, we have the Streams and Rivers Assessment Hub, or SARA, which is an iPad application, which is used for the field data collection. And then those data are then also moved up into a geodatabase at the national level and stored and served by the National Operations Center. All right, so now I want to talk a little bit about our commitment to quality assurance and quality control. And we feel really strongly that if you're going to have a standardized monitoring program, it's really important that we also have a standardized policy and procedure to ensure the quality of those data. And so that we know that the data that I collect and the data that you collect meet some minimum level of quality so that we can be very confident in using those data and decisions within BLM, but also serving those data out to users outside of BLM. And so our many steps for dealing with quality assurance and quality control really boil down to 6 broad steps. One is having sound data management plans. The second is training. Third is performing continual data checks. Fourth, taking steps to reduce observer variability where possible. End of season quality control, and then providing other information that aid with data interpretation and context. So before we go too much further, I just want to briefly define quality assurance and quality control. So you may have seen QA/QC, and often those terms are lumped into a single concept, but we like to split them out. And we view the quality assurance as a proactive step of trying to prevent errors from occurring, where quality control is a reactive step of, okay, the errors may have occurred, what's done is done, what's the level of quality of our data, how can we identify some errors and flag them for users, and maybe take some corrective steps where possible. So our data management plans are all found on the landscape toolbox, and in them we designate roles and responsibilities. We describe all aspects of AIM data, so we talk about the sample design information, we talk about field data collection, and we describe some lessons learned from previous data collection events. Our data management plans provide specific instructions for the use of various data management tools that we have, so Sarah and Dima, as well as some plot tracking tools and other tools that field crews may need in the process of collecting data. This management plan are used at all levels, so it's very clear to everyone who's responsible for what and when. And particularly having this timeline figures like this of, okay, here's the flow of data, and this is when I'm responsible for a data component, and then I hand it off to a field crew, and they're responsible for a component of data management, and then it goes back maybe to a project lead, and then the National Operations Center, you know, and it may go around and around a couple of times. But we found that having a very clear data flow, both with timelines and roles and responsibilities, really cuts down on the level of errors in the data. So for those of you who are wondering where these may be accessed, they're all on the aim.landscapetoolbox.org page. And we are going to be in the process of archiving old data management plans. So if you think maybe the data management plan has shifted over time and you want to be able to track the legacy of how we've been treating data quality, that'll be up there. All right, so our next step of dealing with data quality ensuring is training. And there's 3 components of the training that we have. The first is a field core methods course. We offer this for both terrestrial and aquatic. For terrestrial, I think we'll have over at least 9 classes this spring and summer, and aquatic will have a handful as well. At these courses, we go over the field methods and how to do them. We go over the aspects of data management, the expectations for QA and QC procedures. We allow the participants time to practice, and then we also ensure that participants calibrate, both to each other and to the instructors. In addition to the field courses, we also offer a number of webinars dealing with data management, QA and QC, how to use the databases. And we also have quite a bit of online content that can be taken at a more self-paced aspect, and those include tutorials on how to use the databases. We have method videos where we film folks going out in the field and doing the core methods, and we have recorded webinars from previous offerings of those webinars and other training materials, the manuals, all of those are available. And so together, any given AIM crew that's going out has experience some combination of all of this, and ideally all of these in entirety. So in addition to training, we also really enforce continual data checks. So you don't really ever put ensuring data quality on the back burner or on autopilot and sort of set it and forget it. It's something that we're always thinking about. And so we have one of the big pieces we have with that is our electronic data capture. And so by using SEMA or Sarah in the field, those databases have logical checks built in to say, are you sure about that? There's, that really doesn't make sense, and really catch a lot of errors before they occur. It also prevents transcription errors later on. We also encourage crews to do field checks. So maybe after you've collected all of the data, to run a summary report and say, okay, well, we're seeing 45% bare ground here. Does that check out with, more or less what you're seeing? And having the crew be on the same page of the data output that's going to come from that plot before they leave. We also have a number of office checks that are both scripts as well as visual checks of the data. And I will say that all of this is iterative, and we're always learning from the next step below and then going back up and saying, okay, we need to fix the field checking part because we're catching all of these errors in the office. So we also are taking a lot of steps to reduce observer variability, because what we don't want is that in 10 years maybe a change has or has not been detected, but that is just due to the fact that it was a different person going out and measuring and not due to actual real change on the ground. And so one of the steps we take with that is calibration. And so in training and throughout the season, we want to make sure that our field crews are calibrated to the method and what they mean. And if they're not, that we take corrective action to improve those results. So in this instance, we're looking at percent bare ground as recorded from the line point intercept method. And this is data from a training, an initial calibration. And so by and large, most of the group was in this like yellow and green where like they were within our tolerance limits of where we like to see folks. But we also had a number of outliers. And so what we would have done here and said, okay, who are those folks? What was going on that these outliers within what the broader group is calling, what are they seeing? Is the rest of the group missing something that these folks are seeing, or is there some sort of deviation here that we need to work to get our team together? The other thing that we're doing to reduce observer variability is repeat plots and lab testing. So in this case, aquatics has really led the effort here. They have a certain percentage of their plots that every year are revisited by a second crew within 2 weeks, and then the results of those analysis are compared to see, okay, what are the differences between these two crews and what's causing that, and then what can we do to correct those differences, either in training or how we're presenting the method or something like that, and taking corrective action. On the terrestrial side, we focus more on lab testing of soils and trying to understand where our crews falling down in their ability to texture soils. And that's actually led to some really meaningful lessons for us in terms of how we train crews to texture soils and characterize soil pits, as well as some of the common techniques that we've had, say the soil texture ribbon by field flow chart that we've all probably grown up moving through. We've learned there's actually some really key points where people fall off the wagon. And so maybe if we can add a little bit to that flow chart, we can improve the accuracy of the soil texturing by our field crews. So our final step, what's done is done. We do have thorough quality control, and that occurs at all levels. So it starts with the field crews. They do some evaluation of the data and making sure that everything makes sense and the species that were recorded actually could have been recorded in that area, et cetera, and then it flows up through project leads. The state signs off that they've checked the data, and then it comes to the National Operations Center, who does one final check before it's ingested into the national database. As I said, we have a number of error checking scripts that look for missing data and logical checks. This is often an iterative process of looking at the raw data, calculating some indicators, going, hang on a second, that doesn't make sense, let's go back to the raw data. And we go around and around with that. One of the things that we found is really important is that we don't just throw indicators out there without some of either the background of the data quality steps that we've taken or some other interpretation context. And so these are some results from the aquatics repeat cruise where they've started to look at, okay, what are the error rates for different indicators and maybe our ability to detect change by different indicators. And so in this case, if we look at bank full width and overhead cover, those are actually some pretty tight results. And so our ability to detect change based on observer variability is really good. Total nitrogen, there's a lot of variability in those data that may be due to observer variability. And so we need to start working on tightening that up, or that's just a limitation in the use of the data that the user needs to be aware of before they start using them in management decisions. The other piece of interpretation context that we like to provide is in the form of sample design information. And so if what we provide is, okay, these are the plots that the crew was supposed to go to. They only managed to collect data at a certain portion of them. A certain portion of them they tried to sample and failed. Another portion of them maybe were not actually part of the initial target population, even though we thought they were. In the case of aquatics, they tried to sample a stream and it was dry. All of that, it can be really helpful interpretive information when you're using the data and saying, okay, why are those sample locations where they are? So with all of this information in mind, accessing AIM data for your own use is relatively straightforward. Terrestrial data, the indicators are available through the Landscape Approach Geode portal. Or if you want the raw data, you can complete a data sharing agreement with the NOC and get the full geodatabase. Aquatic data at this point is only available via data sharing agreements, but we do hope to have that up on the Landscape Approach website soon. And finally, AIM data is not just an internal to BLM. We're seeing AIM data being used by over 40 organizations, from private industry to other research agencies, universities, across the board. These are all of the folks who have requested a data sharing agreement with the NOC to use AIM data. So it's pretty exciting to see the breadth of the reach of AIM data and know that you're not alone in using the data, and it really is becoming a community of practice. And so we're really excited about that. So with that, any questions? Mm-hmm. It might be helpful to some people who practice right now to have like I'm not sure that we could. I will say we've been building a suite of R tools to work with AIM data, and so then you wouldn't necessarily need an ARC interface and you'd be able to use R. So stay tuned. Hopefully we'll be able to publish that R package sometime in the next year. All right. Thank you.